Okay, so welcome to day 4, everybody. I had a little bit of an adventure. I'm glad so many of you have made it here. So it's my great pleasure to introduce Jenia Tevelev from UMass, who will tell us about semi-orthogonal decompositions of moduli spaces.
Well, thank you so much for the invitation, for braving the elements, this horrible weather to come to my talk. Right, so I will be talking about results from 2 papers, solving a conjecture proposed by Narasimhan. And really, it was a very pleasurable project for me to work on by 2 reasons. One is that I'm a big fan of Narasimhan's work, and kind of nice to understand what he was working on in the last years of his life. And then the other reason is that I'm also a big fan of cultures of the pre-Columbian, pre-colonial Andes, who didn't have mathematics in the kind of Euclidean sense of this world, but they put a lot of effort into developing very sophisticated weaving patterns and weaving constructions. And so it was kind of interesting to me to kind of that I came up with an argument that can be essentially all packed into a single picture like this. And I made a few copies. Pass it back. So move to the next slide, and let's see. All right, so maybe let me start by kind of trying to explain a little bit of a background, especially for younger people, and also to try to explain, why Narasimhan thought about this problem as a very natural problem. Right, so so we start with a smooth projective curve of genus at least 2. So then M, which was denoted by SUC 2D in the Mukai-Stock, will be the moduli space of stable rank 2 vector bundles on C of degree D. So stable means that the degree of every line subbundle of E is at most D over 2, the slope of E. So the degree, so the determinant of A will be a fixed line bundle lambda, and I will assume throughout my talk that the degree of lambda is odd. So this case is easier by various reasons, and actually, as you will see, the convenient choice of this degree will be 2G minus 1. Okay, so why is this such a good degree? So one reason is that there are no strictly semi-stable bundles, so the slope is obviously half an integer, and so n is a projective variety. So the stability implies that there are no non-trivial combs from E to E, and then standard Riemann-Roch calculation shows that x1 from E to E is C3G minus 3, and then this by deformation theory is a tangent space to n E. So we see that n is smooth of dimension 3G minus 3. Another thing, a nice thing about curves is that every curve is an extension. Oops. Sorry. Then it's like a TJ. I'm so glad I prepared this notes for myself. Okay, right, and so then every vector bundle on the curve is an extension of line bundles, and it's easy to see that the general extension of lambda by structure shift is stable, and so this gives a rational map from the projectivization of the space of all extensions into M. And just as easy to see that it's birational onto its image. Lambda is this fixed determinant of E. So, for example, E will have determinant of lambda. So this lambda is fixed throughout my talk. Yeah, and so then if the degrees.
But you said it's stable. Oh, but it's not
General.
And degree of E is 2G minus
1. 2G minus 1, yeah, throughout my talk. Yeah, and so then if we fix the degree to be 2G minus 1, then this space on the left is projection space of dimension 3g minus 3, and this shows that n is a rational variety.
So this is the second reason for the choice.
The second reason for the choice, yeah, there's also a third reason. Maybe I'll come to that. Yeah, and in the even case, which I'm also finishing now with the student, situation is a little bit harder because in this case the natural choice of the degree is 2g, right? And then this map from 3g minus 2 to n for g generically vibration in p1s. Yeah, so we show that n is unirational, but it's an open question still whether or not n is actually rational in the even degree. So that sometimes is known as Turing's conjecture. Okay, well,
there's some construction like that.
yeah. I think the best result known is that if the rank is degree are co-prime, then it's rational. Yeah, there was some prehistory of that, so it's a result of many people. But this by the similar sort of extension construction.
So I'll do just a little bit to
I'll continue. Okay, so now that we more or less understand n, let's try to understand vector bundles on it.
so now they see that's
Okay. So for line bundles, well, this is a classical calculation of Harder and Narasimhan, and the Picard group of n is Z. Right, and well, now we don't see. Now we see that. Right. So the ample generator I will call a theta line bundle, and it's a square root of density canonical bundle. So n is two fun varieties. Okay, now that we understand line bundles on n, let's try to understand rank 2 vector bundles on n. And so here, well, we run into a problem that, of course, n has high dimensions, so it's very hard to construct vector bundles on n. But there is one obvious vector bundle that we have from the beginning. So another good reason why odd degree is better than even is that in this case, well, we have a universal vector bundle on the product of T and n. So in the even case, it's a theorem of Ramanan that such a universal bundle that exists. Okay, and so if you take so being a universal vector bundle, we have evaluations in two directions. If we fix a point of n, right, so then we can restrict it to the curve and get E. So that's the point of being a moduli space of vector bundles. But we can also fix a point on the curve, and then we can restrict to n. Right, and then this gives a vector bundle on n, which I will call the evaluation vector bundle. Okay, so then it sort of looks reasonable, right? That we get not one vector bundle, but a family of vector bundles parameterized by that point, and we can ask, well, if whether this vector bundle actually moves with a point. Because if it does, then C, well, we can expect C to be a component of the moduli space of vector bundles on n, sharing class. And this was indeed investigated by Narasimhan and Ramanan. This kind of famous paper where they introduced Keke correspondences and all that. They gave a positive answer to that, which, for example, gives an independent proof of the Torelli theorem that one can recover the curve from n, and so in fact, even better than that, n and C have the same module parameter G. So now, how to prove something like this, right? So we have that family of vector bundles. So what are the things to check? Well, I mean, if we expect EP to be a stable vector bundle, then call from EP to EP must be C. So we also expect EP to deform. So X1 from EP to EP better be equal to C.
So are there different keys?
No, it's the same curly. So it's same curly. Yeah, so then, it better be unobstructed. So we show X2 from EP to EP is 0. But then also there is a subtlety here that this kind of shows that EP moves in a one parameter family, but we want more, right? right, we wanted to move with a point on the curve, right? There is still a possibility here that maybe EP is the same. They are all isomorphic for different points, and they just move by some very different reason. And the easiest way to roll this out is to compare home from EP to EQ for different P and Q. And then if that's 0, then in fact EP moves with P and not by some other reason. Right. So yeah. So this sort of shows, okay, that well, so we have that variation of moduli. So we also want stability. But in this case, we're kind of lucky because there is essentially only one line bundle to check. So there is a good normalization of the universal bundle to turn its determinant into that theta line bundle, and then stability is essentially equivalent to saying that there is no homes from theta to EP. And then great. So that's we prove all that. And so they checked all these conditions with Ramanan. It's paper 75. Yeah, but then later on, well, you look at these conditions and you realize that okay, I mean, why stop at the homological degree 1 or 2? Maybe we can just once we started talking about vanishing, we can just carry on and compute the same kind of vanishing for in high degree. Yeah, and so that's what Narasimhan did in 2 papers from 2015, where he proved that, well, that's exactly what I said. So that xi from EP to EP is C only in degrees 0 and 1, and 0 if I is equals 2. And also, well, if you take xi from EP to EQ, then it's equal to 0 for every I. And furthermore, xi from theta into EP is also equal to 0 for every I, using the same method of Hecke correspondences and birational games. But so this method, it sort of gets increasingly complicated when you try to do it. And that's why we had to publish 2 papers, one dealing with the case of G at least 4, and one with the case of G equals to 3. Right. So in the genus 2, this was classically well, known by Bond. Okay. And so then, of course, from it's easy to reformulate these conditions using sort of standard language of Fourier-Mukai functors, as we all know. Right. So if we have a vector bundle on the product y and x, so for me y, well, actually there will be different y's showing up. So let me just do it in this generality. So then we have a Fourier-Mukai functor from the derived category of y into the derived category of x, given as usual by pulling up, tensoring with the kernel, and then pushing forward. And under this Fourier-Mukai functor, the structure sheaves of points, the skyscraper sheaves of points, become these evaluation vector bundles that I mentioned previously. So we have this functor, and this functor comes with what's called Bond-Euler-Orlov criterion, which shows us how to check that the Fourier-Mukai functor is fully faithful. So essentially, one needs to check fully faithfulness that all home spaces are the same just on the generators of the category. So one needs to show that xi from between 2 evaluation vector bundles is equal to 0 if points are different, because skyscraper sheaves don't interact on y. So the images by the Fourier-Mukai functor shouldn't interact either. And then home from EY to EY must be C, and then xi from EY to EY must be 0 for I greater than the dimension of y. And there is a little bit of a bonus feature in the Bond-Euler-Orlov criterion that one doesn't need to separately investigate the range between 0 and I. Okay. And so in this language, right, we can say that, and that's how Narasimhan stated it, that Fourier-Mukai functor from the right category of the curve into the right category of the moduli space is fully faithful. Yeah, so I have to say that this was also shown for hyperelliptic curves previously by Fonaryov and Kuznetsov, but that's an even harder method to generalize to things that where I want to generalize.
This is your first component of
essentially, yeah. So that's where it all kind of starts. Yeah, and so then again, sort of, one good thing about having this fully faithful embedding, once the right category of one smooth projects variety into another, is that under this condition, the image of the Fourier-Mukai functor in this category equivalent to dBy is what's called an admissible subcategory. So its injection will have adjoint functors. And therefore, well, like in the Marcus talk yesterday, well, this will give a semi-orthogonal decomposition. Right? So the right category of X will break into the right category of Y embedded by the Fourier-Mukai functor. So I'll just call it like that, F. Just putting the kernel there in SOD and the semi-orthogonal complement, right? So it's then said this starts the decomposition of dBn and splits dB of C from it. Well, so this is actually just about this analysis of X spaces from E to E, but what's the role of theta in all that? Right, so theta is a line bundle on N, right? So we can view it as a line bundle on product of the point and N, right? So then this also gives a Fourier-Mukai functor from the derived category of a point into the derived category of N, right? And extensions from theta to theta are just the cohomologies of the structure shape on N, and N being a fan of the right local sections, which shows that theta is any other line bundle is an exceptional line bundle, right? And so we can also embed the right category of a point using that. And furthermore, the fact that there are no X from theta into EP, which was also part of that generalization of stability in the Racine-Paz work, shows that we already have a two-step semi-orthogonal decomposition of dBn into dBc and dB of a point, and then we need to investigate the rest.
Is there a reason why the rest would be on the left and not on the right?
Well, as your picture shows, left and right is a bit mutatable. So it's you can put it wherever you want. You can put it in between. Okay. Right. And so let's keep embedding, and then so the point is that we have to embed not only the curve but also the symmetric powers of the curve. And so let's talk about how to do that. And so to do that, well, we need vector bundles, but now not on the product of a curve and N, but on the product of the symmetric product of a curve and N. So people working with vector bundles all know tautological vector bundles on the symmetric product of a curve, but that's not going to work because the image of the Fourier-Mukai functor given by tautological bundle will just land in the same category where the bundle itself is the curve. But there is something called a tensor vector bundle, which fixes this issue. So what's a tensor vector bundle? Right. So so we have a product of a curve with itself alpha times, and then we have a symmetric product of a curve, and then we have a quotient by the symmetric group, which has this amazing property that it's flat. And why is this so good? Well, like for example, it means that every base change of this map is also flat because we care not about vector bundles on the symmetric product per se, but also on the product of the symmetric product with something else. We get the family of vector bundles. And furthermore, well, given a vector bundle on the curve times M, so M is here to be, it doesn't have to be N. I mean, I will actually use most of my talk something else. So given the vector bundle, we can pull it back to the usual Cartesian product of a curve using all the projections. And instead of taking a direct sum, which would give us a tautological bundle, if we do that, we take a tensor product of these vector bundles. And so then what this gives, this gives the equivariant of the symmetric group vector bundle on the Cartesian product of the curve with M. And since this quotient map is flat, right? If we just take a push forward of that vector bundle, we'll get a vector bundle on the product of the symmetric product of the curve in F with M. And then taking invariance inside that, the push forward will give us what I would like to call a tensor vector bundle on the symmetric product of the curve and M. So that's sort of the main construction. Well, it's just no, it's easier than that, right? It's just to push forward from product to the symmetric product. Just, and then you take in there. Yeah, you can think about this push forward from the quotient stack by the symmetrical to the yeah. I see what you get. All right. Yeah. So here I just write that if you do exactly the same construction with the direct sum instead of the tensor product, then you'll get what's called the tautological vector bundle, which I'm not going to use. All right, and so we are going to do this for the Poincare bundles. We have this universal bundle on the product of the curve and the moduli space of vector bundles. And so then the tensor bundle, which I denoted as E tensor alpha, will be a vector bundle of rank 2 to the alpha. Okay. And so then here is the main theorem. So this was so that's the theorem that was conjectured by Narasimhan and also by Bellmans, Galkin, and Patti. So what this says is that the derived category of N has a semi-orthogonal decomposition with the following blocks. So one has to take symmetric powers of the curve, and there will be two blocks when K is between 0 and G minus 2, and one block for K, which is equal to G minus 1. And what these blocks are, so these blocks are just given by tensor. Well, there's some kind of a complicated indexing here, but you take tensor vector bundles of the universal bundle, and then you twist them appropriately by powers of the theta line bundle. Yeah, so you can see that there are this kind of four groupings, which I like to call mega blocks.
And these particular twists are in Narasimhan's connection?
No, that's something we came up. Yeah, I mean, he just conjectured that this has to be true, and just based on the previously known motivic decomposition, the moduli space of N due to the albino. And of course, that decomposition doesn't tell you anything about what twists to use. Okay, and so then, yeah, so this is the semi-orthogonal decomposition, right? So as usual, there's orthogonality from right to left, but also like an amazing feature of this is that within each of these four mega blocks, the blocks are just pairwise orthogonal. Yeah, and sort of a nice way to arrange this information to make it compatible with Dubrovin conjectures is to use this result of Muniz, that the eigenvalues of the multiplication by the first chain class of N of quantum homology of N has this amazing shape of a cross. So you have points on the right and then curve at the top and the bottom, and then flips symmetric square, symmetric cube, and so on and so forth. And then you put sim G minus 1 into the middle, and depending on the parity of G, you can kind of line up with horizontal or vertical axis. What's that? Quantum cohomology. Yeah. So the eigenspace will be that one. Yeah, and then you sort of arrange the blocks. So you put the first mega block here, and then you kind of rotate the spiral. The second mega block is here, and then another mega block is here. This mega block is here. And as always, with semi-orthogonal decompositions, and I will come to that. There are various mutations. You can rearrange things in various ways.
Already, this is the centers which you block in projective space to get N.
I will get to that on that. Yeah. Yeah. So exactly as Jenia is saying, to understand all that, well, we need to resolve the map from the projective space to N. Right. So the story here kind of starts with genus 2. So that's the classical paper of Newstead. So when the genus is equal to 2, then the story is well known, right? So you have a P3, and then you have a curve, genus 2 embedded into P3 by the linear system K plus lambda. And so then what you do, you blow up C. So you get an exceptional divisor, and you get the M, which amazingly is also a Fano variety of Picard number 2. And then you play the two-ray game with it, right? It has another contraction. And what this contraction does, it's a map from M into the intersection of two quadrics in P5. And from that point of view, you're blowing up the line in that intersection. And intrinsically, as a locus in the moduli space, this line is a trivial locus. The locus of vector bundles with at least, actually, in fact, exactly 2 sections in this case. Yeah, so that's the picture in genus 2, and analogous picture is known in every genus, maybe first due to Bertram, but we need slightly better version of it because we need a factorial interpretation of that fun variety so that we can play similar games on M viewed as its own moduli space. Factorial, in a sense, I'm going to explain, not just not just some random fact. Of course, as was mentioned previously, every variety represents some factor, but here we need something better than that. Okay, right, and yeah, and so this was done by Tadeusz, I guess first in every genus, a very nice paper in Sionis in the 80s. And so what this M is in every genus is that it's a moduli space of stable pairs. So what's a stable pair? Well, you take a stable vector bundle as before, and then you just add a section to it. And you look at the pairs, and the section should be rich. And here, just as before, I'm fixing the determinant of the stable vector bundle, and I'm assuming that this determinant has a odd degree, 2d, which is 2g minus 1. Right. And so then in every genus, M is again a smooth Fano variety, card number 2. So just from the definition, it has a contraction, right? So we can forget the section. So this gives us this map theta from M to N, which is kind of an amazing map, complicated map. So it blows down a single divisor, I'll call it Z, but then it blows it down to the Birational locus, the locus of vector bundle in N with at least 2 sections. And this is sort of a difficult part of this whole story because this Birational locus very much depends on the curve, unlike various other things about N. So yeah, so it's not a blow up or anything like that. It's just some kind of complicated morphism, right? So the fibers of that morphism over the Birational locus are exactly this sort of, well, I want to say linear series, but it's more like linear series for the rank 2 vector bundle. Okay, yeah, and yeah, and one more thing. So it's a fine moduli space. So there is a universal pair on the product of a curve with M. But because you're sort of adding a section, it's not exactly the pullback of the universal bundle on the moduli space of rank 2 bundles. You have at least by minus of that divisor that gets blown up. Yep.
So what's the, so you alluded to this, what's the structure of Z? Is it a projective bundle? Or?
No, that's what I'm saying. Very much not a projective bundle, right? So it's sort of generically a P1 bundle, right? But if you go to further strata, right, where you have, yeah, then it very much depends on the complex structure of the curve. So it's a complicated thing.
The section up to scale. Section is up to scale.
Yeah, up to scale. Well, so it's, yeah, because you do that modular automorphism, right? And then sections become up to scaling, but amazingly you kill automorphisms of P itself. So this is actually kind of nice because this, unlike the modular space itself, where you have to take rigidification, to get the variety, here you don't have to rigidify already. So this is already a smooth algebraic variety. Using section kind of makes things much easier. Okay, and so this is sort of so this is sort of one contraction that M has from M to N. But then there is another contraction. This is a Picard number 2, and this other contraction, well, it's a sequence of flips, and it can be described using the variation of moduli of stable pairs. So we can consider a more general moduli problem. Where again we take a pair, so the vector bundle and the section as before, but then we also introduce a real parameter sigma, and then we change the stability condition. So now the stability condition is that if you have a subbundle, line subbundle in F, then its degree has to be, well, less than or equal than the slope, but then plus or minus sigma, depending on whether your section is contained in L or not. So that's the moduli parameter. And then if sigma is very small, then really it's just the same stability parameter as before. So that's why so M, when sigma is close to 0, just gives you what I said before, basically a pair of a stable vector bundle in the section. But then as you increase sigma, you get sort of easier and easier moduli space. Right, and in fact, what you get is this famous Tadeusz diagram of flips. You know, that you start with M, which has a contraction to N, and then you do flips with flips with flips, and then at the end you get the blow up of the projective space in a curve. And then you know what these flips are. They kind of similar. So if you look at the wall, maybe I'll write it below, but or maybe I'll just write it below. I think I had somewhere how the other flips look like. And this is the picture of the effective cone decomposition of that Fano variety M. So here we have 0. So here we have E. So this is the exceptional divisor of a contraction to the projective space. And here we have Z, which is an exceptional divisor of a contraction to N. So that's the motor locus. Right. So then here, well, here we have a map to N, well, given by 2. And so then on the walls, we have certain maps, certain singular JT quotients. And then it will be very important for my talk. There is a kind of a wall here, which is outside of the effective cone, you know, given by powers of the determinant of F, of the universal of that evaluation bundle of F. Remember, F is different from E, so it has a different determinant. It's not theta, and this is a very important line bundle. Okay. Any questions so far? Okay, so to explain the method, let me try to reprove Narasimhan's theorem. So instead of working directly on N, I'm claiming that in fact, if you do the Fourier-Mukai transform with kernel F from the curve into any one of these MIs, you know, then this functor is already fully faithful. And then if you go all the way to the end of that, there is really on the last moduli space, this will be just a pullback from N, and so this will show Narasimhan's theorem. That is fully faithful. So we can proceed by induction. So we can start with M1. So M1 is just the blow up of the curve in the projective space. And so here, well, so that we have a nice description of the derived category, right? So we have an exceptional collection on the projective space, it's variance on exceptional collection. And then we are blowing up a curve. So we have a lot of torsion categories, DBC, depending on the dimension of C in M. But that's sort of not what we want because we are studying the Fourier-Mukai functor given by the universal bundle, right? Not that torsion, not the torsion category. So now this E, what is this E functorially, right? So functorially, this E parameterizes vector bundles which don't split as the structure sheaf and lambda, but instead those are the vector bundles with the section actually has vanishes at a point. So you have extensions of a slightly different nature, and that's a good way of thinking about the whole Tadeusz tower, that you allow the section of a vector bundle to have more and more zeros. So on a one, they can have just one zero. Right. So then on the other hand, well, we have a universal section of the universal bundle, right? And this vanishes on this loci that we'll also try to generalize later on. Right. So this is the locus inside the product of a curve and the moduli space parameterizing points in sections where the section vanishes at the point. Well, and it's a rank 2 vector bundle, right? And it has a section, and that's where the section vanishes, and the vanishing locus of that section, well, has codimension 2, right? Which is great news because then we can use the Cajou complex, right? So this whole structure shape of that locus is resolved, by the Cajou complex in the derived case of the product of C and M1. So So one can also sort of restrict it to each point on the curve, right? So it's inside the exception divisor, we have a fiber of the routing, EP, this projective space. And then the structure shape of that routing will be resolved by an even easier looking Kožul complex. Structure shape, the evaluation bundle, and its determinant. Yeah, and so then what do we know, right? So we know that this locus D11 is the Orlov kernel, right? For the Orlov blow-up theorem. So basically by definition of the, right? So we know that homes between structure shapes of these routings are just exactly as they're supposed to be in the modular of faithful criteria. But what we want the same statement for the evaluation bundles, FP and FQ. Yeah, but but one is resolved by another, right? So we have this complex, and so well, every graduate student can do that. Well, we just kind of compare cohomologies between the middles of these complexes and sheaves that are resolved by those complexes to conclude, right, that in fact our home between the evaluation bundles, has the same properties. So in fact, the Fourier functor given by now this universal vector bundle from DBC to DBM1 is indeed pretty faithful. And in fact, one can generalize that because when you try to prove this, you realize that you have to prove various vanishing statements. And in fact, what you have this basic crossword mutation, right? And like you can find it on the diagram. It's a very basic mutation. So you start with a semi-orthogonal decomposition of that sort, where you have two line bundles and the torsion block. And then a miracle happens that these line bundles are orthogonal to each other. So we can just interchange them into all and lambda star. And then this torsion block just kind of goes under these two threads and reappears on the other side and becomes the Fourier-Mukai kernel given by the universal bundle. So that's the very basic crossword mutation. I mean, you can find it on that diagram.
So you are first mutating it through O and then mutating it through gamma.
I actually prefer to mutate it like this and then like this because I'll show a generalization in a second. Yeah. Or you can just mutate directly under, hide everything.
So
it's a braid group, right? So,
I see. So yeah, I mean, if you pass it under, it doesn't matter.
Yeah, that's how I draw it. If it passes over, then you're not changing. But if you pass under, you do the mutation.
But what I'm saying is, you can view the mutation by moving the thread either way.
Yeah, if you want to do it exactly, you can move it this way, or you can do it this way. But here and here, you get different kernels. Okay, but this was only part of what we wanted because this shows us that the Fourier-Mukai, this Fourier-Mukai functor into the derived category of M1, but we want to go all the way from M1 to Mg-1. And so how to do that? Well, fortunately, there is this Windows machinery that makes this really something that now I'm even working with some undergraduate students who can do that. So it's really very straightforward. So we have this wall crossing between Mi-1 and Mi. And on the wall, we have certain singular GIT quotient, which contains the symmetric power of the curve. And then we have this kind of a standard flip, or rather this way, I guess, is anti-flip, where we anti-flip one projective bundle over the symmetric product, the other projective bundle over the symmetric product. And in this case, well, so it's interesting. So that there is this kind of a stack that contains both Mi-1 and Mi. And so the objects that we consider, this universal bundle, the tensor bundles, they all kind of functorial, so they all well defined on the whole stack of
on X modulo PGL.
On basically on X modulo PGL. And under this condition, well, by applying, well, it's basically a theorem of Telemann that one needs to apply because we need something stronger than what hyperelastine theorem is. So we get what's called what in this case one could call Windows equality. So if you have some object on the stack X mod PGL2 or X mod PGL, whatever that large PGLN is, so then for this object, well, you can restrict it, to the sort of the locus that you flip, and compute its weights. And then, so the weights will be so a certain collection of integers. And if this collection of integers is within certain limits, very explicit in this case, this is sort of like the weak of the window. Then what one can do, one can compute R gamma on Mi. And so then the first inequality tells you that instead of computing R gamma on Mi, you can compute equivariant R gamma on X mod PGL2. And then another Windows inequality tells you that you can then go from X to Mi minus 1. Right? And at the end of the day, computing cohomology on Mi becomes equivalent to computing cohomology on M minus 1. Once you manage to verify, this Windows inequality. Of course, every problem has its own Windows inequality, but in this whole crossing is particularly simple. Okay, and so in our case, all we are studying is this universal pair, this universal bundle, and it's a rank 2 vector bundle. Its weights are 0 and minus 1, and so then, well, just plugging it in. Well, so what we want really are not the weights of F, because we're computing our home from FP into FQ. So we really want weights of FP star tensor FQ, but then okay, so this will be 0 plus or minus 1. And you will easily convince yourself that these weights are within that range of the weights, right? And so the Bond-Larolov criterion, this computation of our home from FP into FQ will be the same. When you started on M1 and then go all the way to MG minus 1, and so that's great. So that immediately gives us the result.
Like morally, this flips, the category gets bigger all the time, or one piece appears, another piece appears.
So in this walk crossing category grows.
Because these are anti-flips.
Yeah, you can put it this way. Yeah, exactly. Okay, so let's try to generalize this now. The technology cooperates.
People can see your slides no matter what we see.
Yeah, but you can't. Okay, so now we have this tensor bundle function, right, from symmetric powers of the curve into dB of M. And so to apply Bond-Larolov criterion in this situation, we really have to understand these tensor vector bundles better, right? So what they are. So we take some divisor of degree alpha, effective divisor of degree alpha on the curve. And then, well, so the easy case is when the points are all different in the divisor, because then if you evaluate these vector bundles on D, you'll just get a tensor product of evaluated vector bundles corresponding to the points. So that's the simple case. But as soon as points start to collide in the divisor, things get a little bit more complicated. But what helps a lot in these calculations is that even if the points within this divisor have repetitions, this vector bundle on M, on this modular space of stable pairs, is still a deformation of a tensor vector bundle in a very strict sense, so over the line, right? So basically, the zero fiber will be this FD guy, and then all the general fibers will be isomorphic to that tensor product, like that. That's configuration. And so sometimes one wants to do a little bit better. We want to maybe split just one point from D, right? D as P plus D prime on the curve. So then I don't know how to prove another statement, but what I can prove is that FD is a stable deformation. So this is a rank 2 to the alpha vector bundle, and it will be a stable deformation of the rank 2 vector bundles and rank 2 to the alpha minus 1 vector bundle, whereby stable deformation is kind of like analogous to stable rationality. I mean, a direct summand in the deformation of a bunch of copies of this vector bundle. Since typically we use deformations because we want to use semi-continuity, the stable deformation of a vector bundle is just as good for computational purposes as the usual deformation. Okay, and so how can we use that semi-continuity? Right. So we already saw this locus D1. So pairs of points in a section such that the section vanishes at the point. Right, so this divisor can be introduced not just on M1 but on every MI. So on M1, this is this exceptional divisor, so it's a vibration in projective spaces. If you do it for higher I's, it's more complicated. It will be a vibration in moduli spaces, not in projective spaces. So it will be a vibration actually in moduli spaces of stable pairs, but for a different determinant, depending on the point. But you still have that inductive structure on that locus.
MI is also the modular interpretation.
Yeah, all of these guys have modular interpretation for this varying stability parameters. Yeah, and this loci that you have, at least for a point, but also for every alpha, you have that again, this kind of vibration structure where the fibers are also moduli spaces, but for a different version of the degree. Yeah, and so then, well, you can try to play the same game. So now this is sort of in the first paper of the Sebastian Torres where we did all that. So one can take, maybe a Kojoule complex again, just for a single copy of a universal vector bundle, and then, we can maybe restrict, you can imagine restricting some tensor bundle to that, while getting some kind of a complex of vector bundles. But the locus where you restrict to, well, it will also have a module interpretation, be again a moduli space of stable pairs, but just for a different degree. And so then one can imagine that sort of we can try to write all possible vanishings we could, using these Kojoule complexes and windows. And then what we get what we call a hard vanishing theorem on the moduli space of stable pairs. So don't bother with this indices. I mean, they're kind of complicated, but they're forced on you by these windows inequalities that we are trying to use. And so the bottom line is that there is a huge amount of vanishing on M. And here, this works, not just in degree 2g-1, but on all degrees even or odd, as soon as d is at most, well, 2g even actually, once we relax this to 2g, between tensor vector bundles and tensor vector bundles twisted by powers of lambda. And so once when you try proving all that by induction, remarkably, after a lot of work, everything reduces to just a vanishing theorem for line bundles on M. Right. So remember that I had this picture of an effective cone and this line outside of the effective cone, and basically what's true, where everything boils down to just a vanishing of all these vector bundles on the green line. With all powers of lambda from the positive power of g-1 to the negative power of minus g-1 have all vanishing cohomology in all degrees.
X is n. What it says effective fx on the right.
Yeah, it's fm. M. Yeah. Right. And so then again, it's actually a remarkably difficult theorem apparently. I mean, it took us, I don't know, it's like 20 pages to prove this vanishing. But it's somehow vanishing still for a line bundle. So it's like a bread and butter of algebraic geometry to do this kind of things. Yes, so maybe I can also mention that the reason Tadeusz himself studied all that is because he was trying to prove Berlin formulas using this technique, sort of computing cohomologies of global sections of theta, which is somewhere on that line here, but at least it's within the moving cone, using they are vanishing, Monroe, and things like that. No, but here we are sort of outside of this range, so none of this kind of a standard techniques actually work. And so we had to prove this theorem that all these powers of lambda vanish. We actually had to really go through the birational geometry of this anti-flips, use things like polar vanishing theorems, like a lot of ratio calculations, but also this is the only part of the paper where we're actually using this narrow-sequence Hecke correspondence. Okay. So now, and also, and when I say this flipping loci, right, so flipping loci basically look like this, right? So it's a generalization of this locus D1, right? So here we take a locus in the product of CK and the moduli space where we take the divisor and the section and this locus where the section vanishes. So this is a very important sort of torsion. This loci and their structure sheets are important in this whole analysis. And so then when you kind of generalize all that, well, you get this what we call this is now coming to the new paper. This is this crossword pattern, that you can see on the handout. So basically what ends up being true is that the Fourier-Mukai function given by all of these TIKs, all of this torsion, all of this natural loci where the section finishes along the divisor are themselves, fully faithful within the range that we care about. Furthermore, when you do this Windows embedding, from the derived category of M-1 into the derived category of MI, the locus just goes where it's supposed to go. So this locus on Mi-1 goes into the same locus in Mi. And furthermore, there is this mutation in the derived category, right? Where here, basically what happens is that on the left, you have the structure shift, universal bundle all the way to some large tensor vector bundle. On the right, well, you have these torsion blocks given by this loci where the section vanishes along some divisor on the curve. And then you do this mutation. So all these guys just go through, they all orthogonal, as the picture suggests. And the only thing that changes is, this torsion block over here, which just gigantically goes under and reappears as the next Fourier-Mukai, as the kernel given by the next tensor vector bundle. Yeah, and the way you prove it exactly is you sort of pull it all the way to the right and then pull it all the way down. And then what you get on the right is also Fourier-Mukai kernel, but given by a certain complex that one can describe. Then essentially like one part of this whole diagram is sort of description of the cohomologies of the terms of this complex, and then the other part of the diagram is the description of the cohomology sheaves of the complex, and you have that gigantic notation. Okay, and so then so then the nice thing about
Who's the lady and why is she?
or I don't know why I wrote. Oh, there is a movie by Hitchcock. Well, because this is the lady, right? So it appears, but then it vanishes. Right. Yeah. So if I just give you this diagram, you'll probably have to do some kind of mental work, right, to realize that. At least to decide when you want it to show up on the left or on the right. Okay. And so then the good thing about these mutations is that they stack on top of each other. Right. And this connects two semi-orthogonal decompositions of the moduli space of stable pairs. So this is the picture in genus 5. That's right. So where at the top, you have these blocks given by this torsion objects, and on the bottom, you have these objects given by Fourier-Mukai kernels given by vector bundles. So that's sort of ideal thing where we want to live eventually in this kind of world. But this still leaves a question about how to get to the top. Right? So if you look at your picture, right, you're somehow somewhere in the middle, right? And, and we still need to get we still need to get there. And that's where sort of very different weaving pattern comes into play. So again? They can look identical. Yeah, they actually twist by a line bundle. Yeah. Yeah, and this block is also kind of identical, but it's a bit bigger. So yeah, it's like a kind of a 3-periodic structure, something like that. Yeah. It's very nice. Yeah, so actually the orthogonality between this guy and this guy, but with Sebastian, when we wrote the paper, we didn't get know about this. So we had to prove it in a different way. We call it easy vanishing because it's very easy to prove. And now this kind of explains why, because things on the top are sort of from the nose orthogonal, and then you do this thing and they reappear at the bottom. Also, you see, there is no interaction between the blocks. Strength. Okay, so how to get there? Well, it's a very different pattern, like basically half of the page. That we have a Faraday wheel. So what's going on the Faraday wheel, right? So if you ignore completely the modular interpretation of M, then basically, you start with a projective space, so it has its standard exceptional collection, the Birational collection. Then you do the Orlov blow-up thing. So now you have a blocks given by the derived category of a curve that sort of come from infinity. So if you ignore all that, then basically that's the decomposition you're getting. So then you do the next anti-flip. The next anti-flip is not a blow up, but it's of increasing height, as Jenia was saying. And so what you're getting a lot of copies of the symmetric square coming again from infinity. Right? So from this point on, we work on M1, but here we start working on M2. And then you have sim 3 again coming in, and then you have sim 4 coming in. So that's the kind of picture. But then what is this kind of a mess in the middle, right? What are these mutations? So maybe it's the easiest to explain in the very first case, where basically what you do, you just flip some line bundles through DBCMC. So essentially just flip a line bundle through a divisor, just using the standard 3-term exceptional collection. And then what you have at the bottom are again line bundles, but now they have a better property. Now these line bundles in the wall crossing, they have correct weights. They have weights 0 and 1. And as a result of that, under this wall crossing theorem, they just go into themselves. So they come from an ambient stack and they have the right weight. So they're the same on the 1 and M2. So that's the purpose of that thing, of that mutation, to adopt everything so that they squeeze through the weights, through the windows. Right, and so here there are actually the accurate trajectories would look like this. That's why they call them the firing twin. Right, so basically, well, this is sort of a plane, and along this plane, well, you have these trajectories, very simple trajectories, S over T minus K. So T is a real parameter, and then K and S are some integer parameters. And then what you have to imagine is that you have these blocks. Right, so basically, each block is the torsion block dkt. Tensored with some line bundle, which depends on the real parameter T. And then these blocks, they kind of just travel in this XT plane. And what happens to them? Well, so this is a precise description of the line bundle, which I'll skip. But then you have to understand what happens when the trajectories cross. And there are two cases here, right? So if the trajectories cross not at the integer level, then these blocks just go through each other. They just mutually orthogonal. But if the blocks cross at the integer level, then the mutation happens. And just because of some kind of features of these Fourier fractions that I learned about in high school, so that's why I kind of was happy to call them Fourier twill, a mutation happens. And what happens is that actually a lot of blocks have to come together on that integer level. So you have everything from dk plus 1, dk plus 2, all the way to the last block. That can potentially show up, and then you have this kind of mutations. I was giving a talk at Sasha's seminar, and he suggested that I visualize it like this. That makes sense, kind of a rotating palm. So this thing goes all the way under, and then this strand goes all the way over. And then you have this kind of rotate your hand, and then the fingers will braid as they braid in that picture. Yeah, and so that's what you do, right? And so then you basically you kind of start with this picture of accurate trajectories, but then every time you have the intersection, you insert that basic mutation, and then you get this picture. That's that.
So each one of these little things is
each one of these little blocks. You see all these little blocks. Right. Each one of these little blocks. This is probably the most complicated one because they involve the most number of strands.
So you have more than 5 fingers.
Well, yeah. Yeah, you can explain it to aliens probably, so they maybe have more than 5 fingers. Okay, and so so I'm almost done. So maybe if you give me 1 minute, I'll just finish with this braiding diagram. Right. So this so this creates the semi-orthogonal decomposition of M, with torsion blocks. So that's why I call the talk semi-orthogonal decompositions of moduli spaces, because as the first step, you have to write down a good semi-orthogonal decomposition of the moduli space of stable pairs before you even start considering the moduli space of just stable bundles. So then the next step, well, this kind of very standard mutation that shows up all the time, just kind of fixed by the canonical class. So you have to do something like that. But there's also a funny thing here. If you notice a lot of crosses, so here I do a little bit of a sleight of hand, and I change the integer parameters, and then blocks just gets rearranged in a better way.
Which culture has carpets like this?
Well, okay, I'll tell you later. Yeah, and then so this produces so this very simple-minded procedure. I mean, this is sort of standard, but it produces the same orthogonal decomposition. Now we had the 3 mega blocks before, but now there will be 4 mega blocks, And now it's kind of better because they're parameterized by a single integer parameter lambda, not by two parameters as before. And for a fixed lambda, all the blocks with a fixed lambda within each of these 4 mega blocks are just mutually orthogonal. And then guess what? I mean, so here you have these guys, and I rewrote it using the universal bundle on the modular space of vector bundles already. So I switched from F to E, right? So there are all these guys, but then, so they look like something that's pulled back from N, tensor theta, which is also pulled back from N, tensor some power of Z, which is a new line bundle on the modular space of stable pairs. And so then blocks, with a trivial power of Z, they will be just pulled back from N. And you count their number, and you get the correct number that you expect, right? 2 times G minus 1 plus 1. Yeah.
About the previous step, the very dense one in the diagram. So are you just repeatedly?
You do the helix certain number of times, and then you rearrange the blocks, and then you do a little bit of an extra helix.
Okay.
Yeah,
So
yeah.
Like
And the goal of all that is just to create the correct number of blocks. So you just kind of play with integers. So this is a simple kind of a process, except for that rearrangement part, which was also kind of interesting. Okay, and so then the last part of the theorem is the kind of the very bottom of this weaving diagram. So that's what I call the plane weave theorem, which is again is a very explicit theorem, which shows something like this, right? So if you have this DBM, the red case of M, inside it, well, it has these blocks given by Fourier-Mukai kernels with the tensor vector bundles. And so now at this point, the picture becomes less explicit because I'm no longer describing the images of the mutation. Up to this point, I had complete control of mutations. But now all I want to do, I want to see what happens if you project onto the semi-orthogonal complement and then just follow some blocks that we have already seen before. And this is a really nice theorem that within a certain range, so the blocks kind of disappear after you project to N, right? So they go into something in the semi-orthogonal complement, but the whole picture is compatible with this map zeta to the modular space of vector bundles, so they just kind of disappear. And so using this theorem and then a little bit of combinatorics, right? You just analyze the very last step, and you basically, so you just take these guys that come from N, and you just move them down without changing them. And so this at the end of the day will be the direct case degree of the modular space of stable bundles. But then using this theorem on the top, all the other blocks, well, it's kind of for symmetry purposes, it's convenient to move them either to the left or to the right. And then what you prove is that when you move these guys to the left, they go into objects in the kernel. They disappear when you take a push forward to M. And then the blocks on the right, well, they disappear after you do the push forward to M, but if you tensor it to the canonical bundle. And so then, the very last step that I'm not drawing here is that one can take this whole thing and mutate it to the left, and then you get something that's pulled back from N, and then you get something that goes trivially when you take compute R zeta into N. And this proves the asynchronous theorem. So this shows both that these blocks have the right semi-orthogonality, that they generate the derived case of N, but it also shows that all the remaining blocks that you get provide the semi-orthogonal decomposition of the complement to the blocks pulled back from N, which also has a very nice description using the theorem of decreasing conflicts by Toda, but that's sort of a different story. All right, let's stop here.
Thank you very much. Questions, comments?
For what? Modular parabolic bundles? Well, so the story is that, another reason why I started to do all this is because, I wrote this paper with Anna Maria Kostrovet at some point, where we did this, found the exceptional collection on M0 in bar, which is permuted by the actual symmetric group, this Ramanin-Orlov conjecture. And this was like the hardest thing I ever done in my life. It took us like 5 years, and we would just get a new trick every day, and then we would just use the trick and then move on to the next trick. And I always wanted to do something maybe similar to the other modular space, to reuse the tricks. And then I learned about this Racine conjecture, but then people thought this maybe difficult to prove. Actually, the first thing, what I suggested to Sebastian as a thesis problem was to do the modular space of parabolic rank to vector bundles on P1 with n mark points, and so then we started to work on that, and then we realized we can actually do the Racine conjecture itself, kind of move beyond that. But having said all that, I mean, I think there was a paper recently by Ponaryov where he suggested the semi-orthogonal decomposition of that thing, which is essentially the same SOD that we were thinking about with Sebastian. And so I think one can prove it using the same kind of methodology, but it will be easier.
Just a clarification question. You have a full semi-orthogonal decomposition of your M.
Yeah.
It's not okay.
And I have many. I have one with torsion blocks. I have one with vector bundle blocks.
But so at the beginning, you were showing us some component of this decomposition of the form sim C that embeds inside this derived computer. How do you prove that all these components form a full semi-orthogonal decomposition? There is nothing.
Yeah, this is a pretty standard by now. This is basically by just using the standardness of these flips. Yeah, so this is where is it? Also, let me get this part of the diagram.
Because you said it's an anti-flip, so a priori there could be more components.
Yeah, but it's a standard anti-flip. So basically, the contraction to the projective space is very simple. Right. So yeah. So this is just this part of the diagram, right? So you start with the projective space, right? That's your derived category. Then you do the blow up, right? So you add Arlov blocks. Yeah. Then you do standard flips. You add these blocks. That's it. Yeah.
So you know that
yeah.
something.
I mean, there are various versions of this result in the literature. One for standard flip, but then what we use is actually the version of that due to BFK, which is more suitable for us. But it's the same result. So it's basically very similar to the blow up. It's just that you had sort of pure blocks. Yeah, but there is analogous picture basically in a very general situation that one can use for all sorts of purposes.
In the even case, you said that you also something in that direction, but the Moduli space is C.
Yeah, but you see, there I'm working with undergraduate students, so it will take a while maybe to get it all worked out. But basically, what's going on in this case is that you have to work in degree 2G, so the one bigger. And then for that moduli space, well, you already proved all that, so there is very analogous kind of wall crossing and all that. So then it's a little bit tricky when you do like the very last step, when you do, this plane weave, because the plane weave really goes to the stack of vector bundles, right? So the coarse modular space itself doesn't carry it. And so then you do that, but then, the modular space is also singular, as you said, right, in the even cases. So then the best theorem we're trying to prove is just to find the semi-orthogonal decomposition desingularizations of that. So there are like 3 known desingularizations: the Shadri one, the Kirwan one, and what's the last one? The Rasimkan Ramanan one, one with 2 authors, including Rasimkan. Yeah, and I think it will maybe give SOD for all of them. But there's something. I mean, it's not as straightforward as this, because you have the blocks. Because you're blowing up, this Kummer variety at some point, so there are all sorts of delicate issues to understand.
So the stack is not the right thing to take?
Well, I mean, you can try, but you'll get some infinite decompositions, maybe, but you won't get full control of it from this, because you're just getting. So this will give you some block in the derived category of the stack, but which is, I think, is enough for. Eventually for completing all these desingularizations, but for the full stack,
More questions? And what about extend the moduli space of its bundle?
We haven't tried that. Yeah.
Because I think that the projection that pieces should be very similar.
One can do Higgs bundles, one can do vector bundles of higher rank. Yeah, I mean, there are also all sorts of things one can do, but I mean, there are a lot of people, so technology is there, so one can just do it. Yeah, as I said, the technology is so far advanced that the even case I'm doing with undergraduate students right now. So, yes. No, it's more basic. Yeah. But regional stability is an interesting question, I think, because you get this SOD for n in this symmetric powers of a curve. So one can try to kind of get the Birational stability by combining stabilities with symmetric powers and try to deform it. I think this would be a very interesting thing to try. But this will be sort of in the spirit of this hyperrealized neural model program. In higher rank, I don't know, because I mean, then so here I'm kind of working with SL2, but then higher rank, one needs to work with, SLR, and so then stable pair itself is not enough. You need some kind of full Borel reduction, so it's not something I'm going to compute. But yeah, it gets harder.